Today's presenters are Bruce Brotherson from Volcraft and Walt Worthley from Valley Joists. Some of the learning objectives for today's webinar will include giving several methods and practices to modify existing joists to increase the load carrying capacity, providing details which are commonly used to increase the load carrying capacity of a joist component. We'll be addressing the realistic limits of modifications with alternatives when modifications are not possible. And finally, we will be showing examples where the joist lengths are altered. We will begin today's webinar, and I'm going to pass controls over to Bruce Brotherson to start the presentation. Thank you. Great.
Good morning, everyone. It's good to be with you again. I hope you're all anticipating a great Thanksgiving. We're going to start today by just kind of a little review of what we did in part one. As was mentioned, this is part two of a two-part series. I'm hoping most of you, if not all of you, were participating with us last month in part one. So what we're going to do in part two, well, in part one, we discussed methods to evaluate existing open web steel joists and joist girders for revised loading conditions. And in part two, we're going to discuss ways to modify open web steel joists and joist girders to increase the load carrying capacity or to repair some damage. And this is in parallel with the Steel Joist Institute publication, Technical Digest No. 12, Evaluation and Modification of Open Web Steel Joists. As an introduction, commercial manufacturing of open web steel joists began in 1923. The Steel Joist Institute was formed in 1928 and has continued to grow, and there's millions of open web steel joists in service today. So part of the, or maybe one of the, a few of the reasons why we might want to evaluate and modify joists could be for building renovations, for additional loads due to such as rooftop units or conveyors. Perhaps there's some derivations or in dimensions of the building. We need to lengthen or shorten some joists, or other things that we didn't contemplate in the original design, or perhaps some damaged joists. One of the things we always need to evaluate when we start a project is when to say no, whether we can fix them or whether they need to be repaired, and when to say yes. And you can see in this slide, these joists were in a corrosive environment, and after a while there was no more joists. And so in this particular case, you know, fixing a joist is not possible. And obviously this is kind of an extreme, but in every case we need to evaluate whether the fix is possible or whether it's not possible. In Technical Digest number 12, there are some procedures that we go through, and also some suggested details, which will probably save you a little bit of time as you're modifying joists. So that's what the attempt in Technical Digest number 12 is, to help you speed up the process and make you more efficient. You can get that publication for $30, and you can order it at the SJI website, which is steeljoist.org. The Technical Digest this is a table of contents of the Technical Digest. In part one of our webinar, we went over chapter 1 and 2, and today we're going to go over chapter 3 through 6. So as a summary for part one, we reviewed how to identify existing joists. We also talked about the design assumptions that are made for the existing joists. We had some examples where additional concentrated loads were added to the existing joists. We also talked about methods of specifying loads to minimize future repairs. We also talked about the length and placement of welds, and also the risk of the repair versus the in-place capacity of the joist. If you need a little help in your evaluation and you need to find out some things about a joist, maybe you don't have the the original, placement plan or contract drawings, and you need a little help on maybe what, who the manufacturer might be, you can fill out this investigation form and send it to the Steel Joist Institute, and the staff there will help you evaluate and get started if you're in a tough place to get started. So, and that's in the Technical Digest in Appendix A, and it's also a form that you can download from the website. So to analyze the joist capacity, a few things to keep in mind. There's pinned, is considered, the connections, the web connections are considered to be pinned in all cases. And for K-series joists, there was a change in the 2015 spec. And so prior to 2015, bending in K-series joists from uniformly applied loads was neglected, provided the top chord spacing did not exceed 24 inches. In 2015, the bending from uniformly applied loads are considered regardless of the panel spacing. However, the K factor in the slenderness ratio is 0.75, similar to a continuous beam in 2015, and 1.0 prior to that. Consequently, a decision needs to be made regarding which spec is going to be used when you're evaluating the joist. Also, for joists, we consider the joist to be a first-order analysis, and then also for eccentricities, they can be neglected, provided for K-series that the 3/4 rule is followed, and that's in the spec. And for other joist series, when the eccentricity does not exceed the distance between the centroid and the back of the chord, that's when the eccentricity can be neglected. Otherwise, it'll have to be considered in the design of the joist that's being repaired. Some things to keep in mind with regard to reinforcing and placement. Things we need to consider is the cost, the time, perhaps the difficulty of the repair, and even the effectiveness of the repair, and then of course the skill of the workman. So all of those things need to be considered when we're thinking about replacing the joist versus reinforcing the joist. I got a couple slides here showing what happens, what a real bad repair is like, and particularly by the field workman. I was sent these slides saying, now what do we do? And as you can see, the inspector on the project, he marked these up pretty severely, saying, this is just unacceptable workmanship. And so so then we had to do a repair to the repair, which really makes a mess out of things. And also the workmanship can actually, if you have poor workmanship, you can actually weaken the joist. And you can see here where this bottom chord, when they were doing the weld, they undercut the chord, which would weaken the chord, and that would need to be fixed, kind of the repair to the repair situation. So when we're considering adding new joists or beams, there are a few things to keep in mind. One is the existing interferences, whether it's piping, electrical conduits, or other things that are going to be difficult to work around if you're going to add a new joist. Removing and repairing this could be a greater expense than the reinforcement. Also, camber may need to be reduced on the new joist because if there's some dead load applied, say a floor, for example, if there's a dead load applied, the joist would be flat, and if it has camber, you're going to have a hard time getting that joist in. One way to help ease the way to get the joist in is to have a shallower joist seat, so the seat depth would be less than the original, and then you can slide that in and then shim the seat up to where it needs to be so it's in contact with the deck. Also, lateral stability of the top chord, need to think about that. That can be done either by shooting pins through the chord to the decking or the slab, or providing additional bridging to provide the lateral support that's needed to the top chord of the joist. A couple things to keep in mind also, and we listed a number of notes that you could put on your repairs, so that everybody that's involved understands where you're coming from. And so we listed a few of some standard general notes that you might consider. One, and this comes right out of the OSHA reg, is no modification that affects the strength of a steel joist or joist girder shall be made without the approval of the project engineer of record. This is specifically in the erection aspects, or before the building is finished. OSHA requires that be done. Also, another possible note is the details used herein were taken from the typical details provided by the SJI Technical Digest No. 12 and require verification and approval by the project engineer of record. And a third possible is all repairs shall be done in a professional and quality manner. Workmen performing repairs are responsible for the workmanship of the repair. Obviously, in those previous slides, you saw where the workmanship wasn't very good. We want to make sure that people doing that are responsible and capable of doing the repairs. Also, a note on the steel strengths. All steel should be minimum yield of 50 unless noted otherwise. That's just a general note. Certainly, if you were specifying 36 KSI material, that could be used as well. All welding shall be performed by a welder currently certified in accordance with AWS requirements. Welder must be qualified for the welding positions required to properly install the reinforcing. Quite often in a repair, it's going to require overhead welding, and we want to just make sure that the welders that are doing that work are qualified for the AWS requirements to do that kind of weld. All welds shall be made using E70 electrodes, just stating what essentially what the repair needs to match your design assumptions. So that's why that's a good thing to say. And repair shall be inspected by an AWS certified weld inspector. If that's the case, if you want to have somebody look that over, then that's a good note to have, so that it gets looked at. Those repairs that I mentioned before, of course, the AWS weld inspector looked at those and said, hey, this is just terrible workmanship and something else has to be done, which is much better than having the crisis at that point as opposed to sometime later when the joist fails. Also, field repair procedures, kind of a step-by-step of what you're expecting the guys in the field to do. As an example, if we were going to be adding additional webs to a joist, this could be used. Measure length and cut reinforcement angle to proper length. If that's going to be done in the field, that's a good thing to have them do the first thing. Second thing is place reinforcing angles on sides of damaged web and use this material 2x2 by quarter. And in this case, I listed it as 36 KSI. Third is to weld reinforcing angles to cords in accordance to provided repair sketch. And then number 4, remove damaged web without damaging joist cords. Obviously, we don't want to remove the damaged web before we put the new material in there, and so a step-by-step procedure sometimes alleviates some problems in the field. Also, show the location on the joist where the repair is needed. As you can see in this case, we're going to repair web number 8 and web number 7R. And that's helpful for the people in the field to know which webs we're going to look at, so that they do the correct work where it's needed. Also got some samples, repair sketches that I just wanted to go through real quick. As you can see, we've got this reinforcing web. We've called out that the reinforcing web should be essentially 3/4 of an inch from the heel of the cord. That gives them a good idea of, and that helps you understand how much weld is going to be available, so you can place the weld appropriately. And then also notice that these webs have been coped on the ends. That's a good visual for the guys if the coping is needed due to the welding. And then also a weld symbol saying how much weld is needed at each end of each angle. Also, if we're going to tack the webs to the existing web, the new webs, the reinforcing webs to the existing web, that's a good detail. It's also good to show that on a crimped web that those webs are intended to be touching the existing web. And then also when we're talking about reinforcement placing on the top chords, if those copes are needed, particularly so that you get the weld that you need, get the proper part of weld, then that needs to be specified. And in this particular case, we noted what was correct and what wasn't correct. So starting in Chapter 3, we're going to talk about design approaches for strengthening joists. And really, there's kind of two design approaches. The approach one is to ignore the existing member completely and simply design the reinforcing member to carry all of the loads that are required. Approach number two is to make use of the strength of the existing member. So you kind of have the existing member carries a certain amount of force, and then the reinforcing member carries carries the additional required force. So in either case, we need to look at a couple things. First, the cost of the materials for reinforcement is insignificant when we compare it to the cost of the labor. So typically, what we try to make the reinforcing material is as uniform as possible. It is safest to reinforce the joist in a shored position. Welding can generate enough heat to cause temporary loss of the steel strength, and transverse field welds should be avoided. Another is best to reinforce the members with the dead loads and live loads removed. Sometimes that's possible, sometimes that's not possible. But you can jack the joist up to a calculated deflection to help remove the loads when possible, and then pay close attention to the eccentricities caused by the reinforcing. Those eccentricities can actually cause the joist to act a little differently than what our design assumptions are, so we need to be careful of that. In approach two, it is assumed that the applied forces are distributed between the existing member and the reinforcing member. So we're going to use a direct proportional to their areas, and Walt's going to go over that, but I'll show you an equation how to do that. If joists are short to remove existing load, then the preload is 0. If the joists are not short, then we need to calculate a preload based on the load present at the time of the reinforcing. So we're going to talk about that a little bit, and then shoring and jack replacement is the responsibility of the specifying professional. We don't want to leave that up to the guys on the site. That type of thing really needs to be looked at by an engineer or somebody that has a little more technical knowledge than the guys out in the field typically. So when we're going to look at the reinforcing of a tension member, for example, this is what we need to do. The first thing we need to do is determine the total area. So we're going to do this proportion of areas and proportion of loads. So in this particular case, we're looking for the total area required based on the forces, both the piece of O, which is the original force, piece of P is the preload, and obviously that's going to be some sort of assumption based on shoring or other characteristics, and then piece of T, which is the total required strength. And so we put that into this equation, and we get the total area. And we're assuming that existing steel and reinforcing steel both have equal yield strengths. So if they're built out of 36 KSI, then we're going to say the reinforcing material is also out of 36 KSI material. But we can look at it when we have a design procedure when the yield strengths of the two materials are not equal. And there, we can assume both materials have the same yield strength, as I mentioned before, and usually the lowest is the best, and that's the most conservative method. Or we can use the actual yield strength of each material in the design. Allow each material to receive the full allowed stress, and we have a procedure for that. And there again, we go back to our equation. So A sub R is the required area of the reinforcing material, and then the force in the reinforcing member equals equals A sub F over A sub T. A sub F is the area furnished by the reinforcing, or excuse me, A sub FR is the area area of the furnished reinforcing, and A sub T is the area of the existing member plus the area of the furnished reinforcing, so the total area. And then we get this, the force in our reinforcing member. And Walt's got an example on that, so I won't go into that too deeply. And so then when we go through approach number 2, the procedure is to select a trial reinforcing member. And like I said, don't make it easy. Make it available material, and try to use the same material for each one of the repairs, particularly the repairs of the webs. Try to use the same material, and that simplifies it quite a bit. Item number 2 is check the buckling strength of the composite member. If a preload exists, determine the magnitude of the compressive stress in the existing member due to the preload. And then for the buckling check, use Fy as the minimum of what's shown here. And design the weld. We always need to remember to design the weld for the reinforcing member. And the force in the weld essentially is the same portion equation that we talked about before. Okay, we're going to go into some, just kind of show you some examples of some repairs. So typically, both chord members on, I'll call them modern joists. Chord members of modern joists have angles with a gap between the angles. So when we look at chord reinforcement, typically top chords are more difficult to reinforce since the floor or roof deck is usually in place and causing a little bit of challenge for the geometry. And typically with top chords, we're going to have to do some overhead welds. The bottom chords are a little bit easier because the access is better. And with bottom chords, we try not to have overhead welds because in most cases, we don't need them. So here's an example of reinforcing in the top chord. And simply, we put a rod in the heels to add more area to carry more force in the area where the top chords are overstressed. And so here's a simple repair. It makes it easy if the webbing material is placed between the chords, and then we've got plenty of room that we can add these reinforcements. Here's another, if we need a little more material, here's another example where we're putting some plates underneath the top chord angles. In this case, we're calling out some overhead welds, and we can't put plates on top of the joist because we're assuming that there is some deck on top of the joist. And that's going to alleviate, or is going to eliminate that opportunity without removing the deck, which is kind of a big deal. Here's another example. We're adding a little more material still, or we're adding angles. That weld, both of these welds, these are really tough welds to make, and so if these reinforcing angles are very large and protrude out from the outstanding leg of the top chord, that's going to be a real hard weld to get in there. So this is you kind of got to look at this one and say, well, is this really possible? And then if your chords are big enough, then you can lay additional angles in and box them out, and sometimes that's a good option as well. As you can see, in most of these situations, all of the welds that are going to occur to the top chords are going to be overhead welds, and so we just need to make sure that the workmen are capable of doing that. Okay, here's some pictures. As you can see here, we've got some webs that go right up to the outstanding leg of the top chord, and so it's going to be a little bit difficult to get some reinforcing in on that outstanding leg. And so a typical thing to do is to cope off the webs a little bit. Cutting them to a 45 degrees is not going to decrease their load carrying capacity and gives us an opportunity to get those rods in there and make those welds. In this particular case, you know, if those webs are right up tight to the chord, you may not be able to make a to get our reinforcing plate as tight to the vertical leg of the chord as we'd like, and so in that particular case, we can notch that plate out so that it goes around those diagonal webs. One thing to keep in mind, particularly when we got rods that we're reinforcing the chords with, we need some continuity with those rods, and so we may need to, if they're really long, we may need to splice them so that we get continuity in the reinforcing material. Typically, you can get material in 20-foot lengths. So if you needed a 20-foot length, or if you need something more than a 20-foot length, you may need to splice it. But 20-foot lengths are pretty common. It's real kind of difficult to manage if you got 20-foot lengths, but it is possible to get them at 20-foot lengths. Talking about bottom chords, here you can see we're going to put some plates on the bottom chord, and that makes it a little easier because the bottom chords generally are more exposed than the top chords, and we don't have to put in overhead welds. We can extend the plate beyond the edges of the bottom chord. One thing to keep in mind is where the web weld locations are. When we're talking about crimp webs or webs that are welded between the chords, the heavier line here shows where those welds would be placed. And so sometimes we need to verify how much good weld we have on our repair, and so that may need to be done by somebody out in the field, and this is kind of a good place to note where those welds might be, and then how much weld would be there. It's really easy to do web reinforcements on rod webs because they're interior of the webbing, and so, or the round webs are interior, and so you can just lay the reinforcing angles on the outside of the existing webs. And also you can see in the top chord in this particular case we got rod reinforcement there, and so it's pretty easy to get that in. As mentioned in that previous slide, you might want to have a dimension here showing how far down those webs can be so that the rods can get in and not have interference. You don't want to necessarily put the webs on and then have to do some modifications to get the reinforcing for the chord in. So just something to keep in mind, and also that helps in your when you give a step-by-step procedure. Here's some examples of what's been done. As you can see in this case, we've got a rod web joist and just diagonal webs welded to the outside of that. Pretty simple repair. In this particular case, we need to look at the crimped webs, and you can see if we were going to reinforce, hope you can see my cursor, but if we were going to reinforce this particular web, which is a crimped web, we would need to possibly move this pipe support over so that we could get our reinforcing web in there. There again, here we've got some just typical details that you might think of, and please note that in not all cases do you need to cope the ends of the reinforcing web, but in a lot of cases it is going to be required, and that helps you get better fit up and get more weld where you want it to be. As you can see in this case, that there was not a cope made, and so in that particular case, the web's going to be down a little bit, and the weld is going to be, as you can see, the weld's going to be on both sides of the angle and also on the end. And this shows a good point here also, is that the reinforcing angle is butted right up tight to the crimped angle. Sometimes, you know, if a member gets damaged, you may have to cold straighten that crimped member so that you can get the reinforcing member in. And if it's bent too far, and you may need to remove it if it's going to be a detriment to the reinforcing. Here's another little trick to get more weld length on a crimped member. And so in this particular case, we're reinforcing the crimped member with a plate, and then in order to get the additional weld that we need, we're going to add some rods there to get that weld on the outside of the cords and weld it up there. So that's a slick little trick if you need that. If putting reinforcing, you know, just angles on the outside isn't going to work for one reason or another. For webs, you can also put rounds in those diagonal webs. The real trick there is to verify that you have enough weld, or you can add additional weld onto the diagonal existing webs to carry the required force. The joist manufacturers only put the required amount of weld on the end of the web members. That's the way the spec reads, and that's what's typically done. So you may not have full capacity of the angle in the welded connection. So that's always something that needs to be checked and verified. And here's an example of that. As you can see, the rod has been placed in. They're not continuously welded. They're just intermittently welded and then welded at the ends. Diagonal web reinforcement is always a little tricky because we're really careful to get that work point over the bearing surface. So in those particular cases, you almost always need to cope that end of the web, and this shows that those copes need to be made, and the eccentricity really needs to be considered in these cases. So look at that and make sure that you can get that. Here's a little trick for adding a little additional weld to an end bar, is essentially adding the end bar and then welding it to the existing end bar and to the cord to get a little more capacity there.
Thank you very much for joining us this afternoon. We appreciate you taking the time out of your day. We're going to move from the second part, and I really appreciate Bruce giving me about an extra 7 or 8 minutes. We're going to get into some number crunching in the second part. We're going to get into the design examples. And within Chapter 3, there are these 6 design examples are given in Chapter 3 regarding strengthening joist, whether it be a K-series, an LH series, or a joist girder. What we're going to look at in this webinar is example 3.5, strengthening an LH series joist with double angle webs. So we're going to take an example, look at a joist, and say, all right, this joist had some double angle webs, and what do we have to do for it? In our example case, in strengthening this, we're given conditions where we're doing a remodel, and that remodel requires additional equipment to be supported by our joists. Our original joists were designated as 32LH 780/4/440. The additional equipment is going to be spread over 2 joists, and that's going to result in a 2,000-pound load located at 7'4" and 12'3". We have our uniform loads in the designation are the uniform design loads required. What we've done is we look back, we've gone and done a little look at our Our design loads found out that yes, these loads are our design loads that we use for the design of the joist do equal the design loads that are required for the joist in the building currently. There's a little note here, load redistribution method's not feasible. We'll talk a little bit about that. We did a little bit about that in the previous webinar. In this case, what we're saying is, well, we can distribute the loads over the two joists. We can't go any further. We can't distribute it to a third or fourth joist, so we're stuck with just reinforcing, or not reinforcing, distributing the load just to those two joists. So we look at our joist again. Here is a load diagram of what we have, our uniform loads on our joist, the total and live loads. We have an additional 2,000-pound load at 7'4", 4'11". We're going to take this, model our joist in whatever design program we're going to use to try to get the forces and members, forces and moments in our joist members. Slow down. So we're going to take that, plug that into a design program, and get all of our forces and moments, and we're going to figure that's already been done. We're going to use that information now to go back and look at these webs. And when we've done our analysis, what we found is that, well, our overstressed webs were double angle members. Okay, the first overstressed web happened to be the end web, which is commonly referred to as the W2, and the required force in that web is 60.5 kips. The allowable force from our original design, which may have been from the manufacturer's calculations or a previous calculation that we did for just the original design loads, we found that allowable force was 56.3 kips for that member. We also found that the first compression web member was overstressed, and that force requires to be 18.1 kips, and the allowable force in that web is 17.2 kips, so we're a little beyond what we want to deem as acceptable. Our original design was using allowable stress, so when we design our reinforcement, we're going to use allowable stress design. So let's get into that double angle web. And I said what we're going to do now is a lot of number crunching, so hopefully follow. If you like number crunching, you'll probably enjoy it. If you don't, just try to follow along and not fall asleep. So we're looking at that W2. The load and tension of the W2 at the time of reinforcing, it was 23 kips. So what we did is we did our analysis. We looked at all the loads that are there now, and that load is 23 kips in the web based on the dead loads and everything in place. Our required force, piece of T, is 60 kips, 60.5. Our original allowable design force was 56.3. Okay, the area of our existing webs, we found that they were 2 by 2 by a quarter angles. So our existing area is 1.876. We can plug that all into this to find out what the area we need. So our required area for reinforcing is our required area for our web is 2.113 square inches. So what is our required area for reinforcing? Subtract that required area from the existing area we need reinforcing area of 0.237 square inches. Because they're double angle webs, remember one of the examples Bruce showed was just add rods to it. So we're going to add 2 3/4 inch diameter rods, place them in the heel like was shown in one of those pictures, and we're going to find out what that area is for those 2 rods. Simply calculating that area, we come up with 0.884 square inches, which is greater than the area we need, so we're okay. So let's calculate the total area we're going to have, and the total area for that reinforcing is simply the angles plus the rods, which is 2.76 square inches. So let's determine, because we're going to need it later, let's quickly determine what the force in the reinforcing member is. And we want to check that reinforcing member. So the force in that reinforcing member, we just take that ratio of the force in the area of the reinforcing member, our total area, and our preload and total load. Take that ratio, plug all those numbers in, and we get the force in that member is 12 kips. And we determine the stress in that member. The stress is simply that force divided by the area of the rods. which is 13.59, and that's less than 21.6 KSI. Now, 21.6 is the allowable stress for 36 KSI steel. So one of the things we looked at, and I kind of didn't mention, but what we're going to look at is say, hey, we can use 36 KSI steel. This is less than the tension allowable for 36. So we're good. Let's use 36 KSI steel for that reinforcing. Now, Bruce did mention you may have to look at, well, what's the stress in each member? The fact that this is less than that 36 KSI, the allowable for 36, we're going to be okay. 36 or 50 KSI material is going to be good. So let's check the end web, the weld for that end web that we're actually attaching that rod to, or that rod, okay? So we're going to, the joint between that rod and the angle, design that weld for that connection of that rod to the angle, is going to be a partial joint penetration flare bevel groove weld. Okay? The effective throw for that is 5/16 times the rod radius, and we can get that from AISC spec table J2.2. Calculate our effective throw. It's just 5/16 times 3/4 divided by 2 for the radius, and we get our effective throw is 0.117 inches. We're going to use E70 electrodes for our weld, and from AISC table J2.5, our allowable strength for the weld is 2.46 kips per inches. Okay. And using that allowable stress from that table, we can get we get our strength of our weld in our joint, and the total length we need for that weld is simply the force in the rod divided by that 2.46 kip per inch allowable. We need 4.88 inches. So let's use 6 inches. We're going to use 6 inches, and that's going to be more than adequate. And we're going to provide a sketch for that in the end. We're going to provide a sketch for our field modification to add that rod to those double angle webs. And here's what it looks like. We have double angle webs in place, and we're going to add our rod to it right in here. Now, that angle could be rotated the way it's shown here with the toe down. It could be rotated with the toe up. It really doesn't matter. We're just going to add that rod in. Now, as Bruce mentioned, we're going to add stitch welds in here. We only need 3 inches at each end. Remember, we said we need 6 inches of weld at each end, but we're going to weld both sides of that rod. So to get 6 inches at each end, all we need is 3 inches on each side of the rod. And then we're going to add a stitch weld in the middle. It's a good safety measure. It's always good to put that in. You may have load reversal. I would mention, we check just tension here. Be careful. If you have a joist that is under uplift conditions, you could have a compression load in here. So you're going to have to check this for compression as well. Now, the angle itself, the angle may have been good by itself in compression. I would note what's shown here is there is an angle here shown. That tie angle is used pretty much every manufacturer when you have double angle webs. When they use double angle webs, will add a tie angle near the mid span. It adds a lot to it'll add a lot to the compression capacity of that angle. So in most cases, you're probably going to see this angle or some sort of an angle has been installed there as a tie angle about at the mid-span of a double angle web. Now, if you're doing that, if you do see it, you can take some credit for it when you're calculating your K/R ratios if your web is under compression. Now, we also have to check and look at the end web design, that weld of the end web, and what's its force required, and do we have enough at the end of that web. So what we remember our original analysis, what we've done is we calculated that we need 60.5 kips. We're going to look and we're going to base our design on a 3/16 fillet weld, E70 electrodes. So that weld capacity per inch, or a 3/16 fillet weld, is 2.79 kips per inch. We need 60.5 kips for our capacity. We divide those two numbers and we get that we need 11 inches at each end of each web. Okay? Now remember, 21.7 is the total force required. We have 2 webs, so that weld is going to be distributed to each end, to each web. So we're going to need 11 inches at each end. Okay, now I'm going to back up real quick. So what we need to make sure of is that what we do need now to tell them is, hey, make sure that you've got a minimum of 11 inches around the end of this web, a 3/16 fillet weld, 11 inches long. Now, if you find out that you don't have 11 inches here, remember, we looked at it as 3/16. We found out, well, this web member was a quarter. We could always increase the weld size to a quarter, or we could add weld along the inside edge at the toe of the top chord or bottom chord to get the weld length we need. Now, last, we have to make sure, let's check tensile rupture, because this is a tension member, because we have a little bit of an offset, the possibility of shear lag. We're going to check and see if there's a potential for that. AISC, we've got to look at our U value. For conservatism, we can take a U of 0.6, or we can calculate it from table 3.1 using the shear lag factors. We're going to select case 2. The U for that weld arrangement in AIC doesn't really address unequal length welds, unequal length welds. So when you have a heel and toe weld, we're going to look and we'll say, well, how much weld do we have? We'll say, well, let's look at it. We can say we have 7 inches on one side, 4 on the other. So we're going to use the smaller of the two, the shorter of the 2 lengths for our L. So our X, our centroid, is the location of the composite section, which is the web and the rod. And the L is the length of our shorter weld, which is 4 inches. So it's 0.25. Our X bar is 0.25 plus the half of the rod diameter, which is 0.625. Plug those numbers in and get ourselves a shear lag factor U of 0.844. So we have to calculate what is our capacity based on tensile rupture. So based on tensile rupture, that equals FU times the effective area, and our effective area is just U times A total, because it's the total area is the A effective area. There are no holes or anything like that, so our total area is simply our effective area is simply U times the total area. Plug in our shear lag factor. Our F sub U for our steel is 65. Our A total is 2.76. Plug those numbers in, we get our P sub N, our nominal capacity of 151. Divide by omega T, and we get our available capacity for our web, and it's 60.5. It's 75.7 kips, which is greater than our required capacity, which is 60.5 kips. So we're good, and we don't have to worry about shear lag is actually good. So remember, we've got we got a compression web that's also is overstressed, and we're going to have to reinforce that. So we're going to look at reinforcing a compression web, and what do you have to consider for that? Well, our design approach is we're going to select a trial member for reinforcing. We're going to check the buckling strength of the composite member. Okay, we're going to determine the magnitude of the compression stress in the existing member, that preload. We're going to find out what's the minimum yield stress in the existing member. And then for a buckling check, what is the minimum yield stress we need to use? And that minimum yield stress is going to be the yield stress minus the stress from our preload. And we're going to compare that to the yield stress of the steel we're using. And then we're going to design the weld for the reinforcing member. And that reinforcing weld, that weld is simply the equation Bruce mentioned before. We'll go through that when we do our example. So when we looked at our first compression web, again, we found out that the force we needed was 18.1 kips. Our existing member we found was an angle 1.5 by two equal leg angles, 1.5 by 1.5 by 0.138 thickness. We did an existing load analysis and found out that existing preload in that member is 6.9 kips. And remember, it's 2, so we're going to try 2 3/4-inch rods for that as well. This is a good rule of thumb when if you've got a lot of double angle members and you're trying to reinforce, try to use the same size rod in all of them. It just makes good sense. It's a lot easier for those field guys to try to find that rod and know they're using the same size in each one. They're not having to go find a 3/4 rod here, a 1-inch diameter rod for this one, and a 5/8 diameter for that. If you can use the same rod size throughout, it's a great help to the field. And the cost of material is going to be minor when you compare it to the labor costs and the possibility of them grabbing the wrong size diameter, calling you back and saying, hey, is it okay for a 1/2-inch rod? So what we're going to do is determine our section properties. Again, for a single angle, for the single 1.5 by 138, the area is 0.395, R sub x 0.463. For the rod, our area is 0.442, and our raised area is 0.188. So for both for two angles and the rod, our total area, we're going to calculate our total area 1.674, and our radius of gyration is 0.35. Now that radius of gyration is about the x-axis for both combined members. Now, this is what our strengthening is going to look like. We kind of got a little head here showing the strengthening, what we want to do. It shows that we're going to show the geometry of our member. In this case, the geometry of this web was horizontal, and our 6 inches horizontally, and our effective depth is 30.028 inches. The centroid of the top chord to the centroid of the bottom chord. Okay, so we're going to use that. We're going to use that information to check our member. So for the compression web, the allowable load is determined from AISC Chapter E. The allowable compressive force is P sub N over omega C. F sub A is that critical stress divided by our omega C. So we're going to work, our AT for our composite member is 1.67, or excuse me, our safety factor, our omega C for compression is 1.67, excuse me. I got a little head looking at the composite member cross section, and our safety factor is 1.67, or our omega value. So let's determine the yield stress in the member right now. So the yield stress in our current angles is simply that 6.9 divided by the area of those angles, and it's 8.73 KSI. Those members were designed with 50 KSI steel. We did some checking, found out from our joist manufacturer that they did use 50 KSI steel for those angles. So we subtract our current preload stress, or current pre-stress, and we get a available yield stress of 4.12 KSI. So we're going to use 36 KSI rods, and we're going to use 36 KSI for our repair. We're going to check it based on 36 KSI, which will make this very conservative. Now, for members in compression, we do have to consider the Q sub S factor from AISC Chapter E, and we calculate that unstiffened element. We look at that 1.5 by 138. Now, we could use, what you can do, you could possibly look at B sub prime, your unstiffened element as being 0.987, but be careful. Remember, you have a stitch weld. So because you have a stitch weld, there is a portion of this where the effective width, that B, the unstiffened element, is 1.5. Where you are welding it, B may only be 0.987. But in either case, if you use this, what we're going to look at is if we use a B of 1.5, our Q sub S for our form factor is going to be 1.0. So our form factor really is not going to come into play in our calculations. So let's really get into checking our member. Our length, determined our length and determine the slenderness ratio for our new member, 87.4. We've checked that against our max, we checked that against the, what not an allowable, but our limits. We found it's less than what our limit is, so we have to use what equation we're going to use to determine F critical. So we calculate F sub B, pi squared E over L over R squared, and we get 37 for F sub B, 37.39. Now, because we're less than our limit, we use F critical, we use AISC equation E3-2, and we're going to use 36 KSI for our yield strength. We're using 36 KSI for yield strength, and we get our critical stress of 24.06 KSI. Our available compressive stress, divide that by omega critical, or omega compression. Boy, I got too much critical, too much compression. We divide it by our compression, omega for compression, and we get an available compressive stress of 14.4. So our available compressive force for our reinforced member is 24.12 kips, greater than our required force of 18.1 kips, so our reinforcement is okay. That compression member is going to be just great for now. So let's determine the force to connect that rod to these angles. And remember, the force is the force in the rod. What force do we need to connect that? So we determine the force in the rod. We use the previous equation where we get a total force, our preload, and the total force is strictly the area of our reinforcing rods divided by the total area. We take our ratio out, and we get that our force in our rods is 5.91 kips. Again, we did calculate those for each 3/4 inch rods. The allowable force in those rods is 14.41 times the area, which is 6.37 kips. So we're going to use this force for our weld design. So the joint between the rod and the angle, again, is a flare bevel groove weld. It's a 5/16 radius based on our previous calc. Okay, the effective throat is 0.117 inch. Our available shear capacity in that for E70 is 2.46 kips per inch. And the required length based on our force is, or our stress is 2.59 inches. So we need at least 3 inches at each end. And we can go back to where we started, our original, where we have our reinforcing rod. We're going to use 4-inch long welds at each end, and we're going to stitch weld it 2 inches at 12 inches on center. So here's what our detail is going to look like. But remember, we do have to check the buckling of the rod. Make sure the rod's not going to buckle before the entire member. So in order to check that rod, let's look at this. The effective length of the rod is just the distance between the welds. That distance is our spacing minus the length, 2 inches. 12 inches minus 2. So our effective length for our rod is 10 inches. Our slenderness ratio is 53.4. So we plug that into our F sub E equation for F sub E, and we get F sub E as 100.09. Determine our critical stress, for the rod is now 30.97. Remember, you were using 36 KSI steel. Our available compressive stress for the rod, simply divide F subcritical divided by our omega compression, and we get 18.54 KSI as our available axial compressive stress, and our available compressive force in the rod is 31.04 kips, which is greater than our required strength of 18 kips so our rod is fine. It's not going to buckle before the entire reinforced section. So that's great. We're all designed. So we've designed our two members, designed our end web and our compressive rod, our tension member, our end tension member, our end rod, they're both designed. Of course, you can use the same approach for designing the top chord. If you have to do an analysis or design of reinforcing the top chord, the same approach can be used for the top chord. Just watch, you do have to watch for what of your unbraced lengths and make sure you're using the right unbraced lengths for the different members. In Chapter 4, we'll talk a little bit about the following chapters. Now we're going to go look at what's in the chapters 4, 5, and 6. Chapter 4 goes for design approaches for modifying joists if you're going to shorten or lengthen a joist. Factors you need to consider in shortening or lengthening, that when you're lengthening, even a small increase in the length can cause a considerable increase in chord forces. Remember, you got a little bit more. Although you may only be saying, I just need to add a foot. You can cause a lot of increase in member forces, especially your chords, and be reinforcing your top or bottom chords where you may not think you need it, but actually you're going to find yourself having to reinforce top and or bottom chords. Careful, because interior webs can go through reversal. You start increasing a length, all of a sudden a tension web can turn into a compression web. Be very careful of that web stress reversal. Camber can be adversely effective if you're trying to once you cut that end web, all of a sudden you may start losing some of that camber that's been manufactured into the joists. If you're removing a main web member, that can also cause a little loss in camber, or you can lose some strength. Now remember, if you're shortening or lengthening, you're probably going to be doing it on the ground. So you may not lose as much, but you can remove, so you can lose a little bit of that camber. You may want to take steps to maintain that camber. You may have to tie the joist down, try to find a way to keep the camber in it. In some cases, depending on how much you have to lengthen or shorten, it may be less expensive just to get a new joist. Manufacturers may just simply recommend, if you have to lengthen a joist by too much, a manufacturer will just recommend replacing the joist. Lengthening a joist 6 inches, a foot may not be too bad, but if you start getting longer than that, the manufacturer's probably going to recommend that you replace the joist. Again, more factors to consider when you're looking at shortening a joist. Generally, when you're shortening a joist, you're not going to have to reinforce the top chord, the top or bottom chords. You're going to need new bearing seats, obviously, and you're going to need new end webs. Designing, make sure you get to design those. Again, when you do cut it, again, you're going to possibly remove some of that camber. One thing we have happened, and some people say, well, I just got to shorten the joist 6 inches, and it's an unacceptable practice to say cut that end web, cut the top chord, and just bend that existing end web back. And this practice has been done usually with a rod, when that end web is a rod. And a lot of them will say, well, geez, it's just a rod. We'll just take it, we'll just bend it back over where it's got to go. That's not an acceptable practice. You're going to put pre-stress in that rod that hasn't been analyzed, and trying to get that rod to work is not a good idea. It is not recommended, and we just say it's not acceptable. Some other factors for shortening and lengthening. When you're lengthening a joist, they may require additional reinforcing of the top and bottom chord, as I mentioned before. To lengthen a joist, you may want to consider adding a splice in the center, depending on how much you need to lengthen it. You may want to splice at an end panel, but it may require additional web reinforcement. Okay? Splice at the end panels generally requires no web reinforcement. So it just depends on where you want to add that splice. Where do you want to lengthen the joist? Typically, it's probably the best idea, if you got to lengthen it, is lengthen it at the very ends of the joist. That's usually, those end panels are usually have a lower lower axial forces in them. So if you're going to reinforce it, if you have to extend it, it's usually better to extend it at the ends as opposed to trying to think about doing it at the center of the joist. If it's possible, if you can change the support conditions at all, modify that, and so you don't have to modify the joist. A lot of times it's not possible to change the end conditions of the structure, but we're always saying, is it possible? What's happened? Usually, if you've got to lengthen a joist, it's possibly because, well, maybe the column's not in the right spot, or the wall, for some reason, the wall got moved, or it's just off location a little bit, and we've got to reinforce, we've got to lengthen that joist. The steps you go through. We'll look at the steps for shortening or lengthening a joist. For shortening a joist, the steps you want to go through is strictly determine the original web layout, look at the top chord end panel length, look at the interior panel length, determine the number of panels, determine where the shortening length occurs relative to the top chord panels, where you want to shorten it, where's your new end web going to start at the bottom chord panel point, and you want to make sure that try to get that angle of that end web to be about 45 to 70 degrees from vertical if you can. If you start going more than 45 degrees from vertical, or excuse me, less than 45 degrees from vertical, you're going to find that it's going to be very difficult to get the end web over the seat and develop a working point over the bearing seat. Determine the loading for that shortened length joist. What is it? Go back, determine that length for that shorter joist. Perform your design for that new length. Compare the material required for the new length. Compare those two materials, all of the forces in your material for the shortened joist, and reinforce any undersized or overstressed existing webs as needed. You're going to have to add a new bearing seat at the top chord for the new location. This is typically a pair of angles that can be welded either outside or inside the top chord, and determine and force in an end web. And typically that new end web could be two new angles. It could be a round bar, a square bar. You want to make sure that it's going to work with your bearing seat. And finally, your bearing seat, typically for K-series joist, that bearing seat is 2.5 inches deep, and make sure that they weld that new bearing seat in at that depth. The steps you want to go through for looking at lengthening open web or lengthening steel joists. Determine your original layout. What are your end panels, your interior panels? How many panels do you have? Where do you want to lengthen the joist? Again, if you can lengthen it, typically you want to do it at the very end of the joist, at an end panel. Look at how much you can lengthen. Sometimes that lengthening based on the slenderness ratio of that end panel. If that end panel gets too long, the slenderness ratio of those end panels long time may govern the size of that top chord. So be careful of how much longer you make that end panel. Also, increasing that end panel increases the length of that new end web. So increasing the length of that end web, you've got slenderness ratios to consider for that end web, especially if you have to be concerned about uplift. So determine the length of that. Remember, determining that when you're lengthening a joist, one of the things we mentioned is that you could get stress reversal in some of the interior webs. When you're lengthening that joist, perform a design for that new length. Find out what the reinforcing member, what forces you have in the existing members. Do any of them need to be reinforced? You can use, depending on what you're doing, you may want to you can use a little bit of a judgment, find out, a little bit of engineering judgment. If you're just a little bit over your 1.0 stress interaction, you may want to be acceptable. That's going to be some engineering judgment you're going to have to use. Place and weld the new top chord angles in to extend that joist. And a lot of times extending a joist means cutting it. believe it or not, you can't just extend that joist and everything's going to be okay. You're going to need a new bearing seat. Many times, simply extending a joist, making a joist 8 inches longer means you're going to have to cut it back and then add that top chord back in. So you're going to have to use a pre-qualified butt splice for welding that new top chord angles in. Make sure you splice that new material and you develop adequate strength. Always recommend, if you're going to splice it in, add a little reinforcement at that splice. It's just a good safety measure to do. It helps just protect that splice just in case, and it's cheap insurance. Again, we're going to have to add a new bearing seat at the end of our lengthened joist. Typically, that's a pair of angles, again, welded outside or inside. If it's a K-series joist, those angles are going to, those seats got to be 2.5 inches deep. And again, we're going to add new end webs, double angles or round bars for those new end webs. We're going to go over a quick example from chapter 4. There's a quick example of shortening a joist. We're going to just go over that real fast. Some of those things we're going to do, what we just mentioned. Our given condition was a 39-foot, 10.5-inch long, 24K8, and it needs to be shortened 10 inches. So our sketch down the bottom shows that joist shortened 10 inches. We modeled it real quick, and we found out that those two webs, those two circled webs, may need to be reinforced. We'll get to that soon. But again, we'll shorten that up, look at our angle, our theta angle, try to keep that. Our new length, our new end panel length was 3 feet 3/4. So we modeled all our new joists for our design loads, looked at our ASD load tables for the joist, and we found that for our original joist, our capacity was 293 kips. So we analyzed that joist for that, our shortened joist, for 293 PLF. Excuse me, I don't know where I got kips from. We analyzed our K-series joist for 293 PLF, and our analysis revealed that those two circled webs were overstressed, so we're going to need to reinforce them. For K-series joist, your webs are most likely all going to be interior, are going to be crimped angle webs. Your end webs, your end web will probably be a rod. It could be a square bar, but a lot of times for this joist, it's probably going to be a rod. So we can reinforce those with just adding angles to the outside. Using that example, that sketch Bruce showed earlier, we can simply design, maybe easiest thing maybe just to design the new webs to handle the total force, and design those new, size those new webs to handle the total force in those required for at those locations. We're going to have to add a bearing seat. Again, these are two figures here that can show what you can do. You can add, typically the K-series joist is a 1-inch gap between the chords. You can use 2 by 2 by 3/8 angles, 4-inch long. The combined, that's going to give you 3/4 inch, which is going to be enough. You could always, they can clamp those two angles, pull them together, and weld them. So the field can always grab these two end angles right at the very end, grab them, clamp them together, and then put fillet welds in here where you don't, so you don't have any gaps. If you do have gaps, AWS allows you to oversize that weld. Those gaps shouldn't be more than about 1/8 of an inch, but AWS does allow you to oversize those, or to oversize the welds if you have a larger gap. You can always use 2 by 2 by 1/4 angles and put a 1/2-inch spacer plate in between, and that'll get you the 1-inch gap. I always recommend just weld them at the toes here and at the toes of the top chord, and that'll get you the weld requirement, get your seat back in. When we did analyze this, we did find that our new end web needed to have a 10,050-pound capacity. Its length was 37 inches. We have a clear length of 2 inches at the top and 1 3/4 at the bottom. We checked our slenderness ratio, and we found out that, you know what, let's use a couple of 3/4 inch round bars. That'll satisfy strength and slenderness. The max slenderness ratio is L/240, or for end webs. Because we're using rods, and again 3/4 inch rods, we are going to have a flare bevel groove weld of those rods to the chords. So the capacity of that weld is 2.46 kips per inch, and we need 4.1 inches at each end. And since we're using 2 rods on each side, we need 2 1/4 inches at each end of each rod. So our analysis was real quick, found out what we needed, and we're going to give them a reinforcing detail, or it's not so much a reinforcing, but a detail to shorten it. So we got our demolition detail, where we have our overall length, our bearing seat. We had 0 TCX here. Typically, I wouldn't do this. I would just take the seat all the way out to the end and just show the bearing seat at the end. But this just shows it just in case you happen to have a TCX. Okay, so what we're going to do is we're going to cut our joist where we need to, cut our end rod out here. Right now we have to cut that web, that end rod or our end web out, and we're going to have to shorten that joist by removing 10 inches, cut the bottom chord 2 inches above. So here's our demolition sketch. Now we're going to have to build our new joist. At the top chord, we're going to add bearing seats. Now again, there's no TCX. If you don't need an extended top chord end, don't show this. Bring the seat right to the end and just show it at the end. This is strictly used as an example in case you need a TCX. Then you need to show how far back that seat needs to be held from the end of the joist. And for those who aren't sure, a TCX is simply an extension of the top chord. So we're going to use, as we said, we're going to use 2 by 3/8 angles. We're going to use them 4 inches long, and we're going to provide section A, where we show a 3/16 fillet weld, welding the 2 angles together. We do have a weld here showing the 2 angles welded together here. It's not really a fillet weld, it's more a seam weld. It's a good idea to put that. You may want to add, and I would recommend, although the detail doesn't show it, I would recommend that placing just a 1-inch weld at the toes here. The detail doesn't show it, but it's good practice just to add just a 1-inch weld in this location. It just keeps these angles from coming out a little bit. It just gives you a little continuity. Again, we have to have now a reinforcing detail for the end rods. So we have a note that tells them place 2 new end webs. They're 3/4 inch diameter rods. You may want to give them a length here. Just give them a length, or tell them, look, you can tell them field cut to fit. Typically, if you're going to do this with AutoCAD now, you can draw these to scale and give them a good length, a reasonably good length, so they can pre-cut them. But have them put the end webs in. Make sure to locate the end webs 2 inches back from the end of the joist, so you can develop the working point over the bearing seat. And we're going to tell them add a flare bevel weld 2 1/4 inches long. Okay, we're going to give them a few other notes. Make sure that all welds are done with E70 electrodes. Fillet welds are equal to the angle thickness. All material is 36 KSI. All welders certified to AWS. Bruce mentioned it's very important, and make sure they're required for AWS. Not just they're qualified welders, but they're also qualified for the positions they're going to have to get into when they're out in the field. In this case, the sketch isn't to scale, so we just made a little note. Hey, look, the sketch isn't to scale. With AutoCAD, it's usually pretty good. It's usually an easy idea. You can usually draw that to scale and give them a sketch that's to scale. It's just something I like to do personally, but that's entirely up to you when you're putting your field modification sketches together. We're going to mention a few things from Chapter 5, some considerations you have to go through, some considerations in making modifications, deflections, camber, effects of the added loads on bridging, and creating 2 joists from 1. There may be cases where you're creating 2 joists, or all of a sudden you need to put an opening. You have an existing joist, and you may find yourself having to put an opening, and this is typically where all of a sudden we're throwing an elevator shaft in, and that roof joist is right where that elevator shaft is coming into. So those considerations, deflections being one of them. Deflection can control. Also make sure to check your live load deflection because deflection requirements could affect strengthening or adding loads to a joist, especially if you've got any added snow drifts if you're lengthening a joist. So be very careful that deflections don't control that. When shortening or lengthening, as I mentioned, camber, you need to try to maintain that camber. When you start removing webs to do either lengthening or shortening, you can take some of that camber out. If you're adding loads to a joist, it can affect the forces in the bridging and can affect the bridging sizes you may need. So also you may need to add lateral support to the compression cords. That's critical that bridging is there because it does provide lateral support under uplift conditions. Refer to the SJI specs for the bridging requirements. Anytime if you're unsure, the specs can give you some good guidance on bridging requirements. When creating two joists out of one, it's similar to shortening a joist if you think about it. The only difference is that you may find that those webs, you're going to get shear stresses or stress reversal in webs, and you're going to get many webs are going to be required to be reinforced. Some other examples in the technical digest regard to changing the natural frequency of a joist or reducing the deflection of a joist girder. There's a couple example of each of those in a technical digest. They're really good. So in summary, we presented some approaches for modifying and strengthening joists. There are several types of reinforcing members, several ways of reinforcing members along with the attachments and their details. Procedures, we've given you some procedures and details to do this, but remember these are not, they do not show every possible way you could reinforce. There is a litany of items you could probably, well, I wouldn't say a litany. There are several other things you can do to reinforce members. Remember, if you start to be creative, be very careful, but make sure you do the engineering. These are simply to provide the designer with some concepts to solve some individual modifications for strengthening requirements, what you have to do. We hope that this has given you some idea of what you need to do to strengthen joists or modify an existing joist. We hope these have given you these procedures have given you that. There are now, the SJI does offer live webinars throughout the year. We also offer in-person presentations. We can be contacted, and these presentations can be designing steel joists for uplift, steel joists and floor systems, an intro to joist, or Joist 101, designing lateral loads, evaluation and modification. All of these can be done. We can do in-persons if you want. You can go to the SJI website to look for more information on this.